Hello, myself Dakshayani C, Assistant Professor of Chemistry, Government College for Women, Mandya. Today we are going to discuss about the chapter Electrochemistry for the course BSc Subject Chemistry, paper Physical Chemistry. This session contains EMF of the galvanic cell, standard EMF, cell reaction, and explanation with the examples, reversible and irreversible cell, and derivation of NERNST equation. First, we knew about there is the EMF of the galvanic cell. In the previous session, already we are going to discuss about what is the meaning of EMF of this cell. So here, that is EMF of this cell, that is we are going to obtain it will be a difference between the electrode potential of the two electrodes constituting a galvanic cell. It is known as EMF or cell potential. It is usually expressed in volts. The galvanic cell, which means we know about that will be conversion of electrical energy, that is from chemical energy. It means the electrical energy which is produced by a galvanic cell given by the product of electromotive force and the quantity of the electricity that passes. If EMF is measured in volts or quantity of electricity in coulombs, the electrical energy is obtained in volts, coulombs, or in joules. Suppose in a particular cell reaction, if it is n electrons involved in the chemical reactions, from that we are going to generate the F Faradays of electricity, then it will be multiplied by the NF of electricity which will be generated from to complete the cell reaction. The electrical energy generated by the cell, which is equal to NFE. So, if it is a reversible cell, if it is a galvanic cell which is a reversible in nature, then it is originate, that is the delta G, change in the free energy with respect to that is the how much of energy which is released. So that will be in the change in that. If you are going to thermodynamically we express that one, which is minus delta G equal to NFE. Here the minus delta G which shows the negative, that is the change in the free energy will be a negative. It means that it is a spontaneous one. The flow of why it will be a spontaneous means, let's say flow of current in the galvanic cell. It is due to that one, that is a tendency of an electrode that is to gain or in a lose of an electrons in that. Each electrode has a different tendency in that, whether it will undergo an oxidation or in a reductions, and that based on that then the cell we are going to set that whether it is in a negative or in a positive EMF. From that we knew about that is whether it is a spontaneous cell reaction or in a non-spontaneous reactions. That is, you know that's whatever the cell here, that is the which is easily that is undergone on oxidations or readily it will undergo get oxidation, means it has a low reduction potential. Before that we knew about a little bit standard EMF. What is the meaning of standard EMF? Means once you know that is EMF means that is a difference in the potentials of the two electrode potential which constitute or a galvanic cell. So that is what we call as an EMF of that one. It is not only a galvanic, any cell, that is what we call. So the electrode potential as you are going to measure at a standard conditions such as 25 degrees degree temperature, 1 atmosphere pressure, 1 molar concentration of electrolyte is called standard electrode potential. It is denoted by the symbol that is E naught. So from the we calculate the standard electrode potential by using a NERNST relationship. So NERNST showed for the electrode potential it is undergone an oxidation, then that will be, or it will be ability to accept an electrons, that one it is deposited, or any one of that's metal that's react with an acid, that will, what is that, it lose an electrons. So what happens to that, whether it undergone a oxidation or a reductions, that one. So here that is the whatever the metal ion, it will accept tendency to accept an electrons and get deposited on the cathode side. The electrode potential at any concentration is measured with the sheet. She means standard hydrogen electrode that can be represented as by using a NERNST relationship for this experimental condition, which is, that is a platinum, that is a hydrogen electrodes on the left side are dipped in the 1 molar concentration of the HCl, and the silver electrode that will be dipped in the AgNO3 of is 1 molar of concentration of this AgNO3. So here that is the NERNST relationship for this a cell reactions, that the EMF of this cell that can be measured by these relations, which is equal to E, which is equal to E naught, that is the standard EMF of that cell, and minus RT by NF into ln of, that will be in the metal electrode, that will be in the reduced over the oxidized state. If it is an R is in a gas constant, T is in a temperature, it is there, N is the number of electrons involved in that, F is the Faraday of electricity, that will be 96,500 coulombs per mole. So here that is when that is the Ag, that silver electrodes, it will be combined with an hydrogen electrodes. The cell EMF of the cell potential, which is equal to plus 0.79 volt, it is in a positive one. If it is a positive EMF of the cell, it means that that cell reactions, it will be a spontaneous. So that is the electrons that will be a flow from left to right here. So left to right means that will be oxidations at the left side and the reduction at the right hand side of that one. So due to this one, because of that a reduction potential, it will be a greater than that of that whatever that be a greater than that, then that is the silver undergo reduction, and hydrogen that will be undergone the oxidation here. So that is will be in the electron flow of electrons, that will be that, therefore that will reflect, that will be, it will be a positive cell EMF of that cell. So if we replace that is a silver from the cadmium, then the same chemical reaction, it is reversible. It is in the reversible process, then only we call as it is a spontaneous, otherwise it is not in a spontaneous reaction. Because of that EMF of the cell, that will be a negative, that will be minus 0.403, it will a opposite directions of that cell. So here in that, why you are going to, it is opposite that one, because of that reduction potential of cadmium, it is less than the reduction potential of hydrogen. Instead of that is the cadmium undergo a reductions, so it will undergo what is that, it will be oxidized one. So what happens to that, in that case electron flow from cadmium to hydrogen, not for the hydrogen to a cadmium. So therefore that is EMF of that cell shows a negative one. The same thing if we replace the cadmium, that will be by zinc. Zinc, it is also a lower reduction potential compared to a cadmium. It will also that will be show instead of it will be undergone a oxidation, so it will undergo a reduction one. So therefore that will, what happens to that will be electron is also a flow from a zinc to hydrogen gas. Therefore that's a hydrogen, it means that CHV, that is the standard electrode potential towards that platinum electrodes. So yeah, that's a, if a zinc electrode immersed in the solution having a zinc ionic activity, it is developed potential, it is minus 763 volts here. So this is the one of the a table. We know that it's the off cell reactions of the silver to a zinc and its corresponding electrode potential. Here that is a silver shows a positive one, that says up to, that will be a zinc, that is a negative electrode potential. Here that is, it will show the magnitude of these electrode potential of these relative strength of the ionic species as an electrons, that is as an accept in the, that is in the decreasing strength. Though silver, which is in a more reduction potential compared to that hydrogen has in a more compared to cadmium, that is as in a zinc, that will be in the a decreasing order. So once you know that, that's why in the AG that will be why it will show the a positive when it will connected with the She, that is a hydrogen standard hydrogen electrodes. In cadmium and the zinc, that will be shows the reversible in the electron flow of electrons, or that is also we called as in the opposite directions. Therefore that will be galvanic cell deflect in the right to left. Reversible and irreversible cell. Your galvanic cell divided into two categories, that is the reversible and irreversible cell. Irreversible cells are those cells which cannot be reversible, or the cell which is not satisfy the condition of reversible is said to be irreversible cell. A simple one, that is the same, just you are going to keep it in mind, that is galvanic cells, that is zinc is dipped in zinc sulfate and copper dipped in a copper sulfate. Instead of that one, if both the electrodes is immersed in a dilute sulfuric acid, if you know about that is an idea about the metal reacted with any kind of an acid, then there will be a liberation of hydrogen gas. That is the same reactions that will happen here. Zinc electrode reacts with an acid spontaneously without any external source. If it is connected to an external source, at anode, what happens to that zinc that will get oxidized, that will be a zinc ions, and whatever that's hydrogen that will be in the hydrogen, that is an acid, that will be accept that ones to give rise to a hydrogen gas there. That's the same thing. If it is increase in external EMF, then what happens to that, that's the same reactions, it will be a reversible in nature. Instead of zinc undergone a dissolutions, it means that it will get into its solution, or an aqueous solution or an acid solution, because of here we are going to take an as an acid. So copper undergone a dissolution here, it means that it undergo dissociate into a copper 2 plus and electrons here. That's the same, that will be irreversible in nature. Then irreversible cell, thermodynamically it is a irreversible cell and it will satisfy the all the conditions of the reversible. Here that is reversibility implies a state of equilibrium at every stage and the occurrence of a spontaneous reaction at the electrodes. For example, that is, we are going to take, and there is a galvanic cell here because we are very familiar with that. The galvanic cell, that cell, that is standard electrode cells of galvanic cell, which is equal to 1.10 volts. This is the, how can we say that this galvanic cell that will be in the reversible in nature. So here, case 1, if we take an external EMF, that is, you know that external EMF means we are going to connect it to the external source. The cell, that is external EMF, you are going to supply the external EMF is equal to the cell EMF, which is exactly equal to the balance the EMF of the cell. There is no current flow. So there should be a no chemical change in that cell, therefore there is no reaction occur. So here, that is whatever they given here, that instead of zinc or a copper, I am going to replace that one into a silver and the copper Daniel cell here. So same thing that will happens in the Daniels and the copper and the zinc is also. In the case 2, that is the reaction is reversible. If an external EMF it is increased by the small amount, the current should pass in the opposite direction, and the cell reaction should be exactly reversible. That is, you know that it will be, it will show the positive 0.4 and 2. That's in a case 2, if an external EMF is greater than, that is the cell EMF. In the case 3, so if the external EMF it is decreased by an infinitesimally a small amount, current will flow from the cell, and the chemical change, that is proportional to the, whatever the chemical change, that is proportional to the in the extent of quantity of the electricity passing should takes place. It means that current, that will be a flow in the same direction. It means that is whatever the current, that will be a flow from there, so left to right, which is equal to the current flow of current from the external source. Next we go for the derivation of NERNST equations. We already knew about, that is the NERNST by using a electrochemical cell or the EMF of the cell that can be easily determined by the NERNST relationship here. In general, for any standard cell reaction associated with, we know that n electrons involved in that, then the change in the energy of that cell already explained. If it is a spontaneous cell, delta G, change in the free energy, which is equal to negative of, that is NF E0. That's E0 means that is the standard electrons of that particular cell. Here, that is whatever the EMF of the cell, that is the intensive properties, and it is delta G is an extensive properties. If it is intensive properties, the and extensive properties, that we have to know about, but is by a thermodynamic relationship. The same argument applies to any cell. If the EMF of the E, that is the Gibbs free energy change, if it's a standard conditions, it will be in delta G. Any cell EMF of the particular, that is delta is equal to minus NFE. So the change in the Gibbs free energy, if for example, then there will be a chemical reactions that will be occurs in that cell, that is the reactant. If you observe, let's say A moles of A and B moles of B, which will give rise to, that's Y moles of Y, giving rise to product, that's a Y moles of Y and Z moles of Z of that product. Than that, by using a thermodynamic relationship by the Van 't Hoff then we are going to write from that equation delta G is equal to delta D naught plus NRT ln Q. Here Q is the reaction quotient. Reactions means that will be how that's a Q, that's a before equilibrium, at equilibrium. So if it is law of mass action, when I apply that one at equilibrium, so then what happens to that? The ratio of that one to the products towards the whatever that will be into a concentration of the reactant at equilibrium, that will be equal to that Kc. We are going to that's a equilibrium constant there. If it is Q, that is the quotient, reaction quotient, it is greater than, and that is Kc, then the reactions, that will be a backward one. It will be a backward one. If it is a Q, that's a reaction quotient of that one, it is less than, that is Kc, then what happens to that? The reactions, that will be in the forward directions. It means that at equilibrium, that will be a equation that will be greater than that. Yes, that will be, what is that, greater than that one. What happens to that? The cell reactions, that will be in the reverse direction. At Q is equal to Kc, that a reactions quotient which is equal to, that will be a Kc, Q is equal to Kc, then rate of the forward reaction which is equal to rate of the backward reactions, that reaction is at equilibrium state. Here, that is a state, they substituting that equations, that is equation 1 and 2 in the equations 3, then we know that that is a EMF of the cell which is equal to this standard cells in equal to nRT ln Q. Dividing on that all those things, then equations become E cell and E naught cell minus RT n ln Q. So this one what we called as an NERNST equations, but that is the quotient before equilibrium, at equilibrium. So here that is the at equilibrium, that is a standard state, that delta G becomes 0 and quotient become its Kc, and where N is the number of electrons that will be in the cell reaction. It is there, that you already knew about that. Therefore, that E standard cell of that one at equilibrium, which is equal to, that's the standard EMF of the cell, which is 0.0591 by N into log Kc. That's we are going to substitute. That's a gas constant, temperature, and Faraday, that is a 96 more 5000 coulombs per mole. So we substitute all those things. The equations become, that is 0.059 and that is a log K. Why you are going to put in Q is equal to Kc here. If an off cell reactions, that is Mn, that will be in the aqueous, that will be zinc, and that will be accept an electrons and it will get deposited on any one of that metal. Then M, that is we are going to take an as an unit. It means it is undergone a reduction, it is there. Therefore, M it is taken up, then that is the NERNST equation we are going to rearrange it as an E is equal to, E standard is minus 0.591 divided by N log of Mn, that is when the oxidized at 25 degree centigrade. For the same thing, if you add take another example for the cell, that is the zinc and the silver, that will be in that another galvanic cells. Here zinc undergone oxidation and silver undergone a reduction state. That EMF of this cell becomes E cell E standard 0.051 to log of zinc, that will be the oxidation one and also reduction. It may be reversible also, that is the depending on the, if we consider the concentration one, depending of the activity of the aqueous solutions of the concentration of that one also, that it can be it will be a reversible, it will be reduction over oxidation is also taking place. It will be like that. not only like it will be oxidized and a reduction, it's some of that will be a reduction and also oxidation, it's also a taking place. There's a overall, that's a EMF of the cell, that will be a combination of both the electrode, standard electrode potential of the zinc and off cell, and also the off cell of standard electrode potential of the silver. So these two electrode potential, this constitute the overall cell. Therefore E cell, which is the combination of the both the standard EMFs of those two electrode potential. This is the problems, how you are going to calculate the equilibrium constant of the reactions if the iron and the cerium, that will be oxidation and reduction reactions that will be undergone by using the calculate the EMF the cell, where that is you are going to get in a Kc, I mean endpoint in that, and the equilibrium constant in that. So for that reactions, you not cell already given for the cerium, which is equal to 1.444 volts, for the iron 0.68 volts here. Solutions for that from the previous cell, that's we already knew, that is the equilibrium constant, that C cell is equal to 0.059, because they are given that will be in the standard potential. Therefore E cell, which is equal to 0.592 log 10 of that, will be a case Kc. Kc, then E cell, which is you already know that 0.76 volts by knowing these two. Then the Kc, which is equal to 0.6 into 2 divided by, because of that will be a number of electrons involved, and that it is from knowing that one, then it is very easy to calculate that, and it will be 25.76. Then the Kc, which is equal to 5.78 into 10 to the power of 25. This is the how we are going to calculate the equilibrium constant for the reactions, the iron and also a cerium in that. These are the reference and sources for the for making this video and also that study material. Thank you.